Okay, so we're going to do the MO diagram for PH3. We could do NH3. I just wanted to pick something that was like ammonia but not ammonia. And the reason we want to do this one is just because it uses those symmetry adapted linear combinations of the hydrogens. Okay, we did that with water, where we had the symmetric and asymmetric versions of hydrogens in water, and we combined those with oxygen. We did that in the notes. And then last week, Friday, we did the nitric oxide, which was really just like a diatomic, kind of like a homonuclear, but it was heteronuclear. And in this one, we're going to have to use those the combination of the 3 hydrogen 1s's that we did with the projection operator. So with the projection operator, we got 3 symmetry adapted linear combinations, but they were 2 different symmetries. And so let's do that today with PH3. So over here on the far right, we'll do phosphorus. And so how do we break this molecule up? We break it up into symmetry groups, right? The phosphorus is the center, so it's unique. And then the H3 is like 3 symmetry equivalent hydrogens. So that's one side of the MO diagram. The other side is the phosphorus. You could do this with like an octahedral complex. It would be really difficult to draw all on one page, but you would have the central atom, and then you have the 6 outer atoms and their combinations. Or you could do this with a tetrahedron, where you'd have the central atom and then the 4 combinations on the other side. So in the middle, we'll have our PH3. So let's draw that the best way we can. This is a wedge here and a dash. And be sure to draw those hydrogens close together so that you can see there should be like one in front of the other. And that's the symmetry axis, the C3 axis. And then coming out of the board is the x-axis, and going to the right is the y-axis. Remember the right-hand rule. So it's x, y, z counterclockwise when the coordinates are drawn in that manner. So that's the local bond theory, Lewis dot structure, 2 electrons on the phosphorus unbonded. Let's do the easy part first. Let's pick the valence atomic orbitals on phosphorus. So we have 3 degenerate p orbitals and an s orbital. And which ones are those? So we find phosphorus on the periodic table. It's on row 3. So that's going to be a 3s and a 3p. And we'll do x, y, z backwards, like x, y, and z. You know, there was some confusion on the homework when I corrected it, but I'm afraid I may have made more confusion. So on the homework was asking about this hydrogen peroxide. Was it hydrogen peroxide? It had Ag and Au and like A1G. And, oh, it's just O2? Yeah, okay. So I said that the atomic orbitals don't have G's and U's. That's overly broad, that statement. Like if it's just an atomic orbital in like an octahedral field or something, like it's the center, it's on the center of mass, then the p orbitals and the d orbitals and everything, they will have G's and U's. But in their diatomic, like oxygen diatomic, when you have the atomic orbital on the oxygen, it's off the center of mass. And so a p orbital by itself over on this oxygen can't really have G or U symmetry until it's combined with the p orbital on the other side. But it is A1. And so that's why if you look at the new diagram, I don't know if you printed it off. If you look at the new diagram, the oxygen orbitals just say A1, not A1G. Like the 2s orbital on oxygen is just A1. It's not A1G. Because when it combines with the 2s orbital on the other side of the molecule, it can combine in a G manner where they're both the same, or in a U manner where they're different. So the G's and U's come when you make the whole molecule. This isn't really an issue for anything heteroatomic because there's no G's and U's. But for that one, when it's so symmetric, you have G's and U's on the molecule, but on the atoms, which are off the center of mass, I just didn't want to confuse you, but I'm afraid I confused you more, because now I'm telling you that they're off axis. We're in a character table that has G's and U's, but you really just need to see that the A1s are going to mix with A1s, and they'll mix in G and U combinations. And then the E's, like E1s, will mix in E1U and E1G combinations. But the p orbitals that are off axis, the px, py, those would be, look at your sheet, is it E1 or E2? I think it's E1, but E1. Okay, so the p orbitals on those oxygens, the px and py, will be E1, but they're not G and U until they mix and make the molecular orbital. And when they mix and make the molecular orbital, the antibonding ones are G, because the shaded regions are across from each other, across the center of mass. And then the p orbitals, the pi orbitals, are U, E1U. So hopefully you see that in the diagram. So I went back and just made the diagram even more accurate as best I could. Okay. So let's go find the C3V character table. I've got it here in the notes. I'm just going to switch to the next page, but if you have your own, you can see here. So here's the C3V character table. And so in this case, the phosphorus is right there in the center of the molecule, but we don't have G's and U's, so it really doesn't matter. We just define the X, Y, and Z orbitals. The PX, PY, PZ, they're going to be E for the PX, PY, and then the PZ is going to be A1, and then the S orbital is going to be A1. So we can label those on the phosphorus. So this is going to be A1, the Z is going to be A1, and then the X and Y is going to be E. I don't think there's a number. Yeah, it's just E. Okay. Now let's go, it'd be nice if we could like switch back to those PowerPoints where we had the projection operator, but what we end up with the three hydrogen orbitals, I'll say from projection operator lecture. We end up with this. So right across from the p orbitals on phosphorus, we'll do this. We have a doubly degenerate set of orbitals, and one of those would be sort of X and one would be Y, and those would be E. And so I'll go ahead and draw the pictures of those. So the PX, so for this one here, it's going to be, I'm going to draw this little cartoon like this. Okay, so do you see the molecule? And then I've got a hydrogen coming out the front, and then one in the back, like that, little half moon, and I'm going to shade the one in the back. Okay. So that's that side, and then this side here, see if y'all remember. You're like, oh no, don't do that. Okay, so here's my little thing. I've got, do you remember the combination that was, not this one, the other combination? So let's just say we labeled this as HA and HB and HC. You remember we had that one combination that was two, 1SA minus 1SB minus 1SC. Remember that? And so let's draw that one. So the 1S on atom A is going to be twice as big. So it's going to be huge, right? And then the 1SB and 1SC are the opposite shading of that. So we're going to have one like that and the half moon, and both of those are going to be shaded. So you see the node is breaking here, and that one changes in the Y direction. So that's why it's the Y one. It's changing back and forth in the Y direction. This one's changing front and back in the X direction. You see those two combinations? So this one here is going to be the 1sb minus 1sc. So those are the E combinations of those orbitals. And down here, the s orbital is going to be squared, you know, x squared, y squared, z squared, all of those things. And it's going to be this combination here. Where they're all the same shading at the same time. And we got all three of those pictures from the projection operator. Remember that? Okay. We'll just draw these real quick. Okay. So we've got 4 atomic orbitals on the phosphorus and then 3 for the hydrogens. So 4, 3, 7. So we should have 7 molecular orbitals. Yes?
Are the y and the x flipped? Because x is coming on the board.
Oh, yeah. I got those backwards. Yeah, let me just redraw them. Okay. Thank you for pointing that out. Okay, so there they are, correctly drawn. Okay. So let's go down here and start at the bottom. Let's combine these this 1s on atom A with the A1 combination, no, 1s, the 3s, A1 s orbital on the phosphorus with the A1 combination of the hydrogens. If we combine all 3, there's no nodes. The electron has the largest amount of freedom, and so we're going to draw our little framework of the molecule. And this one's real easy. I mean, I'll go ahead and draw all the orbitals so that we can see. So we have open circles on everything. No nodes. Okay. We have 3 A1s, and so let's go ahead and combine all of those. And then here we have this Z that's going to start mixing in here. So we'll put these dashed lines here. We'll draw a little line to that Z, the P orbital. We're going to have very little of these A1 character up here because it's so far away. So these 3 hydrogen combinations from the hydrogens are going to have very little influence on that one at the top. A lot of influence or mixing or a lot of contribution to the ones on the bottom. So we came in with 3 A1s. We have 3 A1s in the middle. So let's draw this picture here. Okay, so I'm going to draw the PZ orbital on this one, like this, and the shading is on the down below, and then my hydrogens are all going to still be the same color, but they're going to be all shaded. See how they mix with that PZ with no node in between them? And there'll be a little bit of that 3s in there, and all that does with the 3s is just move the node up or down, depending. And so, so this is 0 nodes at the bottom, 1 node for that one. Let's look at this top one here. I don't know really how to ask the question, but I mean, what picture would you draw, right? We've got the PZ orbital in phase with those hydrogens. So at the top, you'd have to draw it out of phase, right? And so some way you've got to draw the PZ orbital, just shaded on top and not shaded on bottom. And then keep those hydrogens shaded. Does that make sense to you? Yeah. So it's not too bad. It's kind of like Bob Ross. I've got a real low voice today and I'm talking quietly. Shade that little happy orbital in the back. Yes, that's right. Yes, that's right. And the PZ is just not liking those guys. I don't know. Woke up on the wrong side of the bed. Okay. MO diagrams with Bob Ross. I may put that on the video, like thumbnail. Just put a picture of him with the MO diagram. Yeah. All right. This doesn't look anything like, he's very talented, so this is not very nice. Okay. Everybody happy with that? The A1s. We've got 3 A1s coming in. We have 3 A1s in the middle. You know you're done. If you come in with 3, you got to make 3. Okay. Now we'll do the side-on interactions of those p orbitals with the hydrogens. Okay. Which one do you want to do first? Do you want to do X or Y? Thank you. So we got to have as a decision. That's good. All right. So X, that's the one that comes in and out. Okay. So we're going to bring these together. We'll have, we're coming in with 4, so we got to draw 4 in the middle. So they go up and down. I didn't kind of go up very much, but. Okay. So this X, we're going to draw the little framework that we have. Draw that PX, a circle with a half moon behind it. And then that's combining with this X one over here, which doesn't have anything on that hydrogen on the right. And the reason that is because that node goes right through that hydrogen. And an S orbital can't have any P type character, right? An S orbital is a sphere. So if the node cuts through that center of that sphere, that orbital can't pick sides. It's just sort of eliminated. And so since that node contains that bond with that hydrogen, it just doesn't participate in this one. That's why it participates twice as much in the other one. Okay. So then we just draw an unshaded circle on the front and the half moon in the back, and the half moon is shaded. You see how those combine? Just with the same symmetry, X and X, they come in together and they make that orbital. And that's a molecular orbital now because the electrons can go over the whole thing, and that's why it's dropped in energy from the p orbital. And so then we'll do the other one on this side. Draw a little framework. And then this is the PX, so it's going to be open on the right, the way we drew it, shaded on the left. And then we got a big open circle on the right, which you see it interacts with that, and then shaded circles on the left. The half moon is shaded as well. So again, the molecule is all shaded on the left side and all open on the right. And so that's the bonding arrangement. And is it a bonding electron in that orbital energy? Yes, absolutely. It's bonding for all 3, though. You know, it's not any particular bond. So you can't really calculate bond order. But you know that's a bonding arrangement because there's no nodes that break the bonds. Okay. Let's sort of draw a line here out like that, and we'll draw a picture over here. So let's do the anti-bonding ones. Draw a little framework. And this one, and the p orbital on the top phosphorus, we'll still draw it open on the top, shaded in the back, and then we'll swap our circles. So this one's shaded in the front, and the back is unshaded. And you see there's a node there. So So that one's going to be antibonding. It's pretty clear because it breaks all the bonds that it goes over. So that's antibonding, but it's antibonding for 2 of the bonds. Okay, now for the Y, the PY. I'll keep the P in the same direction, but then I'll shade the front of this one. I'm going to like distort it so it doesn't go over. There's no overlap if it's shaded opposite like that. This one's open and the back one's open. So that's crazy. Really ugly, lots of nodes. So again, that's antibonding for all of the bonds as well. We did it. We got all 7 on there. Any questions about how we put those together? If you're wondering about these pictures and you're thinking, how am I going to get those pictures if without the projection operator? They're the same. Anytime you have 3 things that are symmetric, like a methyl group, those are the pictures. You have one where they're all in phase, and then you have 2 where they're not. What about stretches? If we were doing 3 combinations, so the methyl stretches, so you got the hydrogens, they can all stretch together like that, or they could do this. One stretches while the other. I've practiced that well. And then the other one stays put and the other stretch like that, opposite of each other. That's a little harder. Okay, so let me just draw the picture. How about we do that? So we have phosphorus, hydrogen. So I'm just showing you the three-wise combination of vibrations. And so it's all 3 stretching. That's the A1 stretch. And do you see how that's the same as 1SA, 1SB, 1SC? That's if you call these bonds R1, R2, R3, then that would be the vibrational wave function would equal R1 plus R2 plus R3. Sort of showing the radius or the bond length of each of those all stretching. And then up here, this one would be so this one right there would be twice this, so a really long arrow on that one and some short arrows on this one. So you see they're compressing while that one hydrogen is really stretching. See that 2R1 minus R2 minus R3. So it's the same, that 2 minus minus is the same. And then you kind of 3 ways combination. And then up here, this would just be like R2 minus R3. So this bond wouldn't stretch at all, and you would just have this one stretch out and this one compress at the same time. And so you see that same thing, all of this combination is all pluses. This is plus 2 minus minus, and then this one, that first one is missing, and it's the second minus the third. And that's, you see that mathematically in all of the combinations that have threefold symmetry. Okay, so let's put the electrons in here. How many valence electrons do we have for the phosphorus? We have 5. Okay. So 1, 2, 3, 4, 5. So that would be the alpha filling scheme for phosphorus. And then for hydrogen, these combinations, we have 3 because we have 3 1s orbitals. So we have 1, 2, and 3. So we have 8 electrons. Isn't that right? 2, 4, 6, 8. Yeah. So we start at the bottom and fill them up. So 1, 2, 3, 4, 5, 6. Look how I did that to get to 6. So you would use the same kind of thing where Hund's rule, you keep them unpaired as long as possible, and then you start pairing them up. So that's 6, and then we pair them up. 7, 8. Okay. So everything's all paired up. So this is diamagnetic. Okay. Okay. These two right here, since they're the same energy, would be the HOMO. These two right here, since they're the same energy, and the next level up would be the LUMO. Let's label, we didn't label the symmetries of our molecular orbitals, so let's go through and do that. You know, A1s were mixed to make this one. The next one's A1, and then this top one is A1. Okay, everybody cool with that? And then the other two are E, so E and E. Bond order can't really be calculated. If it's a diatomic, easy. Yeah, you got it. Discrete, orbitals that are absolutely bonding or absolutely anti-bonding because you only have one bond. But for this, what are you going to say, right? Like this one right here, I mean, you could kind of say that these are bonding or anti-bonding, but it's just when you get beyond a diatomic, just don't worry about it. Yeah. And then let's do the symmetry setup for the HOMO to LUMO transition. So we see that the HOMO and LUMO are both E. So let's go to our character table and do the symmetry of this one. So here's our character table. We have, I'll just do it on a different page. Okay. So the symmetry setup for the HOMO to LUMO transition. For the transition dipole moment integral is that, okay? So it's an integration of overall space of these wave functions. We have 2 wave functions, and we have light. Okay, that's h nu for light. Okay, so the symmetry of the highest occupied molecular orbital is E, and the LUMO is also E. And we go to the character table, and we see that light can be E or is A1. So we'll do 2 problems. So let's do A1 first. That's the simplest. So that's the Z polarized light. And then over here we'll have X, Y. Okay, so we go to the character table and or the direct product table, but we know that A1 times anything is that thing. Okay, so we get E here. We bring the other one down. E times E. Okay, we should remember that. I mean, eventually you do this enough times, that's a set of 3 things. And one of those things is going to be A1. So we could stop the problem right there and say, absolutely, it's going to be allowed. But let's go ahead and look up the other 2. Does everybody remember without looking? Yeah, A1, A2, and E. That's great. I'm proud of you guys. A2 plus E. Let's just go check our work. Yeah, so A1, A2, and E. So E1 times E1. Now this isn't specifically for the C3b. Well, it says C3b character table, and it has E1s in there, but the reason it's for all of these is you can use these combinations, like C3b doesn't have B's, and so you just ignore these two columns for C3b. Okay. But if you see E1 times E1, you get all of this, but there's only an E in this table, and so the 1s and 2s really don't matter, but you get that same combination, so that would work. The bracket, I have to go back and look that up. We've never really used the bracket. I don't remember what that's supposed to signify. So this is A1 plus A2 plus E, just like you guys knew from your memory. And then we're looking at that A1, so we could circle that just to tell DW on the test that we see what we see. And so this is going to be equal or not equal to 0? Correct. It's got an even function in it, and so that means it's not equal to 0. Therefore, what do we say? Allowed, yeah. By symmetry. All right. Now this one is probably going to be allowed too, but let's go ahead and look at it. We got all those E's in there. Surely there's going to be an A1 left over, right? So E times E, we know that gives us that set of A1 plus A2 plus E. And because we got that E there, we're going to get an A1 at the end. But this one is kind of a nested problem. So it's got a big set of results because we have, 3 doubly degenerate things multiplied by each other. So E times A1 gives E. Okay, E times A2. Oh, gee, I got to go look that up, but I think it's E. So let's look at our direct product table. A2 here times E gives E. Yeah, okay. Oops, wrong way. And then E times E, we just did that one, gives A1 plus A2 plus E. So that's the full set. Boy, I would hate to see that integral in real life. Just to write it out would probably be a whole page with all those terms. And the E terms are functions of X and Y. So that's going to be a real messy thing. But we see A1, thank goodness. Okay. So that's not equal to 0. And you got to keep those angle brackets on there because that tells you they're doing an integral. Remember, it's like a mathematical operator. And so therefore this is allowed by symmetry. I used cursive. Oh my goodness. It's like secret code now. Some of the schools don't teach it anymore. You know why they quit teaching cursive? Because of the little writing test that the students had to do and get it graded. And the handwriting was so bad that the graders couldn't grade it. They'd get these essays and they were like, what is this even? And so they just started teaching printing so that they could grade the standardized tests better. So talk about the test. That's the tail wagging the dog. Like you'd lose a whole set of cultural knowledge just because the grading of the standardized test was more difficult. Yeah. So anyway, so our school here taught it as sort of an add-on. The teacher had the cursive conquerors or something like that. And you could turn in some little essays in cursive, and she would grade your cursive penmanship, and then she would give a dinner at the end for all the students that got their cursive under their belt. That was pretty cool. I say cultural knowledge. It's true because you go in a museum and you look at Sam Houston's letters. If you don't know cursive, so it'll be strange. All right, so that's a side trip. Anything that I didn't cover that you guys are curious about? Because, like I said, my brain's kind of foggy. And so we got our pretty pictures here. Yeah, it doesn't really work with the polyatomic molecule like this. Yeah, we can kind of look at this and see that this molecule kind of looks like pi character, right? The p orbital is acting sideways with those s orbitals. And so that's maybe what I would call it. It's not a pi bond. but it has pi character and that the p orbital is acting on its side. But like here, it's not. Here, it's aimed at those hydrogens and aimed at that hydrogen. So, yeah, it's not. The sigma and pi really only matter when you have. I can't say just diatomics because obviously there's pi bonds and benzene and things like that. They're really clear in like planar structures. So you know, if you've got, you know, if we were to take a molecule like this, right? So butadiene. Let's just go onto a new page and talk about butadiene because it's a complicated molecule, but it's not too bad. And so if we were to draw this molecule, I'll go ahead and draw the hydrogens just so you guys know what's going on here. It's been a while since organic, right? Organic chemists are lazy because they don't draw hydrogens on anything. So you can tell them I said that. Well, you know how to say people are lazy and chemists are people. So, okay, so in this molecule, you've got, let's just draw the z-axis coming out. Because it kind of has a C2 axis, a C2 right here coming out of the board. You see that right there? The center mass of the molecule has a C2 coming out. That's the highest order symmetry axis in this molecule, so that'll be the z-axis. And so in this case, all of those orbitals that come out of the plane are pz orbitals. And so in this case, they clearly interact side on with each other and give you pi bonds. So this molecule has clear pi bonds. And so we could draw them if we turn this molecule sideways. So we'll turn this sideways and we'll draw carbon, 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 carbon. Okay. So I've just sort of drawn a scheme where they're all side by side. We have 4 pz orbitals. This is totally legit, like for your level of chemistry. So we come in with 4 pz orbitals, and we got to have 4 molecular orbitals to make with these. So how would we mix those pz orbitals? Let's do it. So down here at the bottom, we have carbon, 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 carbon. What do you think the lowest energy structure is going to be? All bonding. So all our 4 pz orbitals are on here like this. Go ahead and draw them really quickly. I'll put the shading on the bottom for whatever reason. No reason in particular. There we go. So see, no nodes. Those 2 electrons can travel over the whole molecule. Really low energy, big box. Okay. The next one will have how many nodes? Right. So this is the one that you might think is the only one in that molecule. If you look at the Lewis dot structure, draw our 4 p orbitals. And you just switch to them and put that node right in the middle. Piece of cake, right? And then the next one will have 2 nodes. So how do I do this one with just 2 nodes? Yeah, the middle 2 are the same. So the middle 2 will be the bonding ones, and then we'll have a node out here on the outside. And you know where this is going on the 4th one. Got 3 nodes, so We just swap them on every one. We have 3 nodes. And so that has the largest curvature. The box is the same for all 4 of these, but the curvature goes up. The times it crosses 0, the number of nodes goes up. So this are the 4 orbitals. All 4 of these are pi-type interactions. But notice how this one's bonding for all 3 bonds. This one's bonding for 2. So this one is clearly identifiable as that, is what's being represented there. But for the molecular orbitals, we come in with 2 electrons. We come in with 4 pz orbitals for the carbon. I don't know. I can't, without doing the whole molecular orbital diagram, I don't think I can confidently assign the number of electrons to these pz orbitals, but I think it would probably end up being something like this, where we'd have electrons here and electrons here. So this is probably the highest occupied molecular orbital, but I'm not sure. Okay, so I'm going to put a question mark on this thing here. But clearly this would be the pi bonds, and then everything else would be the sigma framework. So the name we call everything else quote sigma framework. So those are the carbon-carbon single bonds and the CH single bonds. So it's like those different types, and those would be the other symmetries of the orbitals. They'd be the 1s's and the px's and the py's all mixing in the plane, and you'd have nodes everywhere and everything like that. And it'd be complicated, although you could do that one. You could probably figure out the symmetry combinations of the hydrogens. How many types of hydrogens do we have in this molecule? And this would help you in NMR as well. So if you can rotate or reflect a hydrogen into another hydrogen, they're chemically equivalent. So they'll have the same peak in the NMR, and they'll have the same combination of their atomic orbitals. Like those combinations will combine. 2 types of hydrogens. You have the closer ones to the center of mass, and then you have the further out ones, I think. Now, it might be 3, but let's look. So I can rotate this hydrogen into that one for sure, and vice versa. So those are the same. So I can put A's on those. These outer ones are connected. But I don't know that I could combine. Like, I don't think I can exchange this one with that one in any symmetry operation, because the molecule is kind of zigzagged in the middle. I can't reflect it this way because the molecule will flip. So there might be C, actually. There might be 3 types of hydrogens. Yeah. And so each one of those would be in symmetric and asymmetric combinations. So that would be an ugly, ugly, ugly MO diagram, but you can do it. What you do is you combine and then there's 2 types of carbons. So you would just build the molecule up pairs at a time, and that's how you would do it. What time is it? About time. Okay. Any other questions? That's a good question. So this, again, these would all be pi bonds. You'd have, and again, even is it pi star or pi, right? Because we got a node here, so it's pi star for that bond, and pi for this. So pi star, pi, which is it? So again, above a diatomic, the pi and pi star, sigma and sigma star are goofy. But you could say for this bond right here, it's a pi type interaction. Yes.
Will we be expected to draw MO diagrams for anything above the diatomic?
I think you should be able to answer questions about one like this, or maybe even draw some of the combinations, but it's a pretty long exercise, and I don't want you to run out of time. So you should be able to understand this one in particular well enough to answer questions about it, or maybe draw a picture or 2. And so, yeah. But this would be the XH3 would be the most complicated I'll take you to. But like, even if I gave you this, PZ orbitals, you've got 4 of them, starting with the bottom. If I gave you the bottom one, could you give me the other 3, or something like that? That's totally within range. Okay. But to start out from scratch with this molecule, yeah, I think there's not been enough time for you to really practice on those. Okay, so see you in a week. Yeah, y'all have a good time together with your family, hopefully. Yeah, take care. Happy Thanksgiving.